Welcome back to the Deep Dive. This is the place where we take a complex subject, strip away all those overly simple narratives, and really try to give you the foundational knowledge you need to be truly well-informed.
It's good to be here.
For a long time now, the whole energy transition has been presented as a pretty straightforward choice, right? Embrace green energy, discard the old. Simple.
Almost like a moral imperative.
Exactly.
Yeah.
But what happens when that simple, morally satisfying story? What happens when it hits the messy, costly, and, sometimes deeply contradictory reality of engineering and supply chains and just fundamental physics?
That reality is exactly what we are dissecting today. We've gone through a substantial stack of research articles, engineering reports, and some really detailed case studies to understand the full costs.
The hidden costs.
The hidden costs, yeah. The challenges that happen, beneath the surface of the Green Revolution. Our mission today is to move beyond the cheerleading and really understand what happens when the theory of 100% renewables meets the hard constraints of, say, grid stability or material scarcity and waste disposal.
So we're looking at the whole picture.
The entire life cycle, from the mine pit all the way to the power line. We're analyzing the full system costs, the geopolitical risks, and these massive stability challenges, using the real-world experiences of countries like Germany and Japan as our guide.
Okay, so to ground this whole discussion, let's go back to an analogy we like to use, the electricity grid as a giant bathtub. You, the listener, you need water, which is your electricity, flowing at a steady rate 24/7.
Right. The bathtub has to stay consistently full.
Always.
Always.
And the total demand in a region is, it's huge. We're talking gigawatts, terawatts, just massive amounts of power. But the principle is simple. Stable supply must meet stable demand.
Now, what we call variable renewable energy, or VRESO, think solar panels and wind turbines, they introduce a fundamentally new kind of problem into that bathtub.
Okay.
They are not steady taps, not at all. They're more like random, powerful bursts of water.
Like someone just kicking a bucket of water in every now and then.
Exactly. When the sun is high and the wind is strong, they're splashing water into that giant tub way too quickly. The grid gets overwhelmed, prices drop. Sometimes they even go below zero.
But the flip side is the real problem, isn't it?
That's the dangerous part. When it's cloudy or the wind just dies, that splash stops completely. And the water level in the tub starts dropping fast.
And that drop is, for a grid operator, catastrophic. So
Right.
What do they need? If they want to keep the lights on and keep that whole system stable, they need two enormous pieces of infrastructure.
The first one is an unprecedentedly large water tower. That's your energy storage. It's
Wow.
there to catch all the overflow during the sunny, windy periods and then release it consistently when the weather is calm.
And the second piece.
And this is the crucial constraint. If that water tower isn't big enough, or if that period of calm lasts for days or even weeks, there's a great German word for it, Dunkelflaut, the dark doldrums.
Right. No sun, no wind.
For days on end. In that case, you need a reliable, always-on auxiliary tap. And that backup power, it's typically coal or natural gas or nuclear. It has to be there, ready to kick in instantly to prevent the bathtub from running dry.
Which means blackouts.
Which means blackouts. And I think the central takeaway for today is that the scale of the storage you need and the physical constraints of the grid itself, well, they make that backup power completely unavoidable for the foreseeable future.
Okay, let's unpack this core issue then, this idea of intermittency. And let's use some hard data, because when you hear a country is installing, say, 100 gigawatts of solar, it just sounds like an immense amount of power.
It does. It's a huge headline number. But the key metric for reliable power isn't the capacity. That's what it can do in a perfect moment.
Under ideal lab conditions.
Pretty much. The real metric is its capacity factor. And that's what it actually delivers on average over an entire year with clouds and night and calm days.
And that's where the reality check comes in.
It's a huge reality check. VRE is inherently intermittent. Production varies constantly, not just day and night, but with seasons, with weather fronts. This is why it cannot reliably provide what engineers call baseload.
And baseload is? Just define that for us again.
Baseload is that minimum consistent level of power the grid must have running at all times, no matter what. It's the hum in the background that's always on, independent of when you turn on your TV or your air conditioning.
And that's traditionally been supplied by things that can just run and run and run.
Exactly. Nuclear, geothermal, or coal and gas plants. Things you can count on. 247.
So when we look at the big adopters, what do these capacity factors actually look like? The German example is probably the most studied.
It is. And the numbers are, well, they're sobering. Germany has poured hundreds of billions into this transition. But the sources we looked at show that their massive fleet of installed solar capacity has an actual real-world capacity factor of only about 11%.
11. So for every 100 watts of panels they install, they're only getting 11 watts of average power over the course of a year.
That's it. And for wind, if you combine both onshore and offshore, it's a bit better, but still only roughly 18%.
So just think about that for a moment. An 11% capacity factor for solar means that for 89% of the year, that hugely expensive asset is either producing nothing or just a tiny fraction of its theoretical maximum.
And you can compare that to a traditional dispatchable power plant. A nuclear facility, for instance, typically runs at a 90% or even higher capacity factor.
So it's an order of magnitude different.
It's a massive difference, and that gap is the fundamental problem. To compensate for that 89% shortfall from solar, you need an equally massive compensatory mechanism.
Which brings us right back to the astronomical need for storage. If your solar panels are only useful, on average 11% of the time, and you want a grid that runs 100% of the time, well, you need the world's biggest battery.
The scale required, it really does move quickly from engineering into the realm of science fiction, at least based on today's technology.
How so?
To compensate for those low capacity factors and to handle those periods of shortage, like that week-long Dunkelflaut we mentioned, where there's no wind and very little sun, the estimates for Germany alone require a storage capacity in the range of 100 to 120 terawatt hours.
Okay, let's pause on that number. 100 to 120 TWH. For most people, myself included, terawatt hours, it's just jargon. What does tera even mean? What does this number represent in, practical terms?
Tera means 1 trillion. So a terawatt hour is a truly massive unit of energy.
Okay.
For comparison, Germany's entire annual electricity consumption is somewhere in the range of 500 terawatt hours.
Okay, so you're saying they need storage equivalent to about a fifth of their entire yearly consumption.
Yes. They'd need enough stored energy to power the entire country for about 73 days, purely from reserves, just to cover those intermittent gaps.
And the key insight from the sources is that this scale, it's just not on the map right now.
Not even close. It would require an expansion factor of several hundreds compared to what is presently available, not just in Germany, but globally.
So to hit that 100 TW8 target, we would literally have to build something that doesn't exist anywhere on Earth today.
Which is why backup power, that other tap, remains completely unavoidable.
Okay, so if we can't build at that TW fate, let's at least evaluate the options we do have for storing electricity. You mentioned 3 main categories in the research. Let's start with the old reliable giant. Pumped hydroelectric storage, or PHS.
PHS is, it's mechanically brilliant. It's simple. You use excess electricity when it's cheap to pump water up a mountain to a reservoir.
And when you need the power back.
You just open a valve, the water flows back down through turbines, generating electricity. It's like a giant water-based battery.
What's the efficiency like on that? Do you lose a lot in the process?
It's actually outstandingly efficient for this scale. You get a high 75 to 80% round-trip efficiency, so you get most of the power back out. And critically, these PHS projects are incredibly durable. They can last up to a century. They are true long-term infrastructure assets.
Okay, that sounds pretty close to a perfect solution for long-term storage. So
yeah.
Why isn't PHS the answer? What's the catch?
The catch is geography. Simple as that. PHS is entirely dependent on having the perfect landscape.
What does that look like?
You need large surface areas with a significant height difference. We're talking a few hundred meters to create 2 massive bodies of water, one high and one low. Usually you find this in a mountain range.
And we've run out of mountains.
We've effectively run out of suitable, available sites. The source material is very clear on this. The required geographical locations for this kind of large-scale capacity are already nearly exhausted throughout Europe. You simply can't build 100 TWh of PHS in a place like Germany or much of Western Europe because the mountains aren't there or the good sites are already developed or protected.
Okay, so that geographical limit pushes us towards the modern high-tech solution. Lithium-ion batteries. They're everywhere now. Our phones, our cars, and now these huge grid-scale installations.
And Li-ion batteries are excellent for specific grid needs, don't get me wrong. They offer incredibly fast response times.
What do you mean by fast response?
I mean, milliseconds. They can inject or absorb power almost instantly, which makes them perfect for handling those momentary little voltage and frequency fluctuations that keep the grid stable. They are the ultimate quick fix.
But they have their own limitations for this bigger problem.
They do. They have a moderate energy density, which means they take up a lot of space and are very heavy for the amount of energy they actually store. And of course, they have a limited cycling lifetime compared to something like hydro. They wear out.
So where do they stand in the grand scheme of things?
Globally, lithium-ion is still a pretty modest player for this kind of large-scale grid storage. Currently, it represents a tiny fraction. I think the number was 0.47% of all electric energy stored in the EU 28 plus countries. It's a rounding error.
Now, the critique here, and it's a fair one, is always about cost. The sources did mention the cost of lithium-ion batteries was expected to drop significantly. It went from about $176 per kilowatt hour in 2019 to an estimated $94 by 2024. That continuous cost reduction is hugely relevant, isn't it?
Oh, it's incredibly relevant, absolutely. But it's relevant for the economic viability of smaller, short-duration storage.
So like a few hours worth of power.
Exactly. Think of a large parking lot battery that helps a solar farm smooth out its production for maybe 4 hours after the sun sets. For that, falling costs are a game changer. But even if the costs are cut in half again, this technology doesn't solve the terawatt-hour problem.
Why not?
Because we don't just need 4 hours of storage, we need seasonal storage. We need power that can be held for weeks or even months to get through the winter Dunkelflaut.
And batteries just can't do that.
Not on that scale. Because of material degradation, self-discharge, and just the sheer physical and financial scale required, lithium is prohibitively expensive and physically impractical for storing energy in June that you're going to need in January.
Which is why the researchers are looking toward the third big option, chemical storage.
Right. This is the concept of power to gas, or P2G.
And the idea here, it sounds pretty elegant, you use all that excess cheap renewable electricity, when prices are negative, to create a storable fuel like hydrogen or synthetic methane.
It is the dream solution for seasonal storage, at least conceptually. You take that overflowing water from our bathtub analogy, the times when power is so abundant it's literally worthless, and you use it to split water into hydrogen via electrolysis.
But there's a catch, and it sounds like a big one.
It's the Achilles heel of the whole idea, efficiency loss. And it's a brutal reality check.
How brutal are we talking?
Right.
What's the loss profile look like?
Okay, so you have to look at the full cycle. You convert electricity to hydrogen gas, then you have to compress it, store it, transport it, and then months later you convert it back into electricity, probably in a gas turbine or a fuel cell.
The whole round trip.
The full round trip. And the sources confirm that this P2G to power system has a very, very low overall efficiency. We're talking somewhere hovering around 15%.
15. 1.5.
1.5, yes. Which means that for every 100 units of perfectly clean, renewable energy you start with, you lose 85 units just in the process of converting it back and forth.
You are literally throwing away 85% of the carbon-free electricity you generated in the first place just to store the remaining 15%.
Yes.
That feels, that makes the whole system massively uneconomical, doesn't it? It doesn't matter how cheap the surplus electricity is if you lose most of it.
It's a huge economic hurdle, and that's compounded by another fact. Generating hydrogen by water electrolysis, which is what P2G requires, is still significantly more expensive than just making hydrogen the old-fashioned way from fossil fuels like natural gas.
So it's both physically inefficient and more expensive.
At present, yes. P2G is currently both physically inefficient and economically disadvantaged compared to just using conventional fuel sources in the first place.
Right. Okay, so let's recap where we are. We have intermittent power, an astronomically large storage requirement, and no existing storage technology that can meet that terawatt-hour scale efficiently or affordably.
Yeah.
Now, we hit what you call the absolute non-negotiable constraint, the physics of grid stability.
This is the critical insight. It's the one that's so often missed in political discussions about energy. Our current power grid operates on alternating current, or AC. And for reasons of fundamental physics, this grid requires mechanical inertia to maintain its stability.
Inertia. You used a great analogy for this earlier. A giant flywheel that absorbs shock. Let's elaborate on that. What does that flywheel actually do?
That flywheel is the kinetic energy that's stored in the massive spinning parts of conventional power generators. Think of the gigantic steam turbines in a fossil fuel plant, a nuclear plant, or a large hydroelectric dam. They are spinning at a precise, constant speed.
Okay.
And that collective spinning mass of all the generators connected to the grid Its stored kinetic energy acts like a giant shock absorber. If a sudden fault happens, say a major transmission line gets struck by lightning and goes down, or a big power plant unexpectedly trips offline,
A whole system could collapse.
it could. But that rotating mass, that inertia, instantly stabilizes the system's frequency, giving the grid operators precious milliseconds to react and prevent a total cascading blackout.
And the problem is that variable renewables like solar and wind, they don't have that big spinning mass.
Exactly. They connect to the grid through power electronics, through inverters. There are no massive spinning components providing that physical inertia.
So what happens when you take more and more of that spinning mass offline and replace it with inverter-based resources?
The grid becomes brittle. It becomes highly vulnerable to shocks. The sources we reviewed show that to maintain stability and prevent catastrophic frequency drops, you need a minimum of 20 to 25% of that rotating mass physically present and spinning in the system at all times.
So if you don't have non-fossil dispatchable sources like nuclear or large hydro providing that 25%, then the system must rely on fossil fuel generators to provide the necessary inertia, even if those fossil fuel plants aren't actually supplying the bulk of the energy.
That is the ultimate conclusion, and it is absolutely crucial to understand. In a high penetration scenario, variable renewables require either a dependable, non-fossil based load source with inertia, or they require fossil fuel backup to maintain the fundamental physical stability of the electricity grid.
There's no way around it.
It's physics. If you try to phase out nuclear and coal without first solving this inertia problem, either with very expensive specialized grid hardware or by keeping massive backup capacity online, you risk the exact kind of system instability that regions like Ireland have seen during periods of high wind generation. Physics mandates the stability mechanism, and today that mechanism is overwhelmingly conventional power plants.
Okay, so we're shifting now from the physics of the grid to the physical objects themselves. The turbines, the panels, the batteries, the sheer quantity of materials needed for this transition. It's staggering. We need to do an honest assessment of what it costs, materially and environmentally, just to build millions of these devices.
This is exactly why the life cycle assessment, or LCA, is so essential. It forces us to trace the entire environmental footprint, from the cradle all the way to the grave.
And what does that life cycle look like for renewables?
The model breaks the process down into 6 key stages. It starts with raw material acquisition, that's the mining, then material processing, then manufacturing, the use phase, decommissioning, and finally, treatment, disposal, or recycling.
And the key point from the sources is that the pollution story doesn't begin when the turbine is built. It starts when the raw earth is excavated.
That's it. At every single one of those stages, you have material and energy inputs going in, and you have environmental outputs, effluents like air pollution, water contamination, and solid waste coming out. This isn't just a problem for disposal at the end. It starts right at the mine pit.
And that mine pit is full of some very specific, very critical minerals.
Yes. For the permanent magnets in high-efficiency wind turbines, for high-performance electronics, and for all of our lithium-ion batteries, we need a specific menu of minerals: cobalt, nickel, lithium, and critically, a group of elements called rare earths like neodymium and dysprosium.
And the demand for these is just exploding.
It is. Driven almost entirely by the planned energy transition, the global demand for these specific minerals is projected to double by 2035.
Doubling the demand for raw materials. That immediately introduces some profound geopolitical vulnerabilities, doesn't it? Especially when you look at where these resources are concentrated.
Absolutely. The rare earth elements, or REs, highlight this risk perfectly. China controls a massive portion of the supply chain.
How much are we talking about?
They control over 95% of global RE production from mines. But even more critically, they control a staggering 87% of the complex processing and refining required to turn the raw ore into usable components.
So it's not just digging it up, it's the bit after that.
The processing is the real bottleneck. And having that concentrated in one country, well, we've essentially exchanged a dependence on politically volatile oil regimes for a dependence on a singular geopolitical power for the critical building blocks of the green future.
And what kind of leverage does that give a country like China?
It creates enormous supply vulnerabilities. We've seen in the past that China has used threats to reduce export quotas as a geopolitical tool. Any disruption, whether it's political or an accident or a natural disaster, in that small number of processing facilities can instantly halt the manufacturing of high-efficiency magnets needed for wind turbines and EVs globally.
So every nation pursuing this has to weigh its environmental ambition against this massive supply security risk.
It's a trade-off they can't ignore.
Okay, now let's talk about the direct environmental costs of getting those rare earths out of the ground. The extraction process is notoriously dirty, isn't it?
It is intensely, intensely environmentally damaging. REE mining requires vast inputs of energy and water just for the physical extraction and then the subsequent chemical refinement. But the biggest environmental hazard is one that often goes unmentioned.
And that is.
Rare earth elements are chemically very similar to and often naturally coexist in the same ore bodies with radioactive elements, specifically uranium and thorium.
Wait, hold on. So you're saying when we dig up the materials for modern high-tech wind turbines, we are also unavoidably digging up radioactive material.
Yes, that is the geological reality.
And what happens to that radioactive material?
The extraction and separation process generates large volumes of waste tailings that contain these long-lived radioactive elements, along with a cocktail of heavy metals and toxic chemical reagents used in the process. The risk profile here is very long-term and very pervasive.
Is there a real-world example of this?
Yes, the largest RE extraction and processing site in the world, Bayan Obo in Inner Mongolia, China, it's a sobering case study.
Tell us about the pollution there specifically.
The operations there have resulted in decades of devastating systemic pollution. We're talking about the contamination of surface water, groundwater, the soil, the air, all across a massive area. The long-lived radioactive isotopes and heavy metals that have been released pose a severe, ongoing threat to local populations, to ecosystems, and to agriculture.
So there's a deep irony there.
A profound irony. The very materials that are intended to support a clean energy transition are being extracted via one of the dirtiest and most toxic industrial processes on the planet.
Okay, let's move to battery materials. Lithium has a different, but you said an equally contentious environmental footprint, particularly around water conflict in some very arid regions.
Yes, lithium extraction in what's known as the Lithium Triangle, which spans parts of Argentina, Bolivia, and Chile, is highly water-intensive. It's not a traditional hard rock mine. They primarily use brine extraction.
Brine extraction, what is that?
They pump mineral-rich salt water, the brine, from deep underneath these vast high-altitude salt flats called salars. This brine is then directed into these massive man-made surface evaporation ponds that can be seen from space.
So they're just letting the intense desert sun evaporate the water off to concentrate the lithium salts.
That's the process. But to do that, you have to use enormous amounts of local water to get the brine to the surface and manage the ponds.
And in a desert, that has to have a huge impact.
It fundamentally impacts the hydrology of the entire Andean salar ecosystem. You're essentially removing huge volumes of water from an already incredibly arid environment. And furthermore, the creation of those vast, shallow evaporation ponds disrupts the delicate ecosystems of the salt flats themselves, including the migration patterns of birds who rely on the natural, often highly sensitive water balance of that region.
And this inevitably leads to social conflict, I would imagine, with local communities who also depend on that same water.
Exactly. The local indigenous communities are deeply, deeply concerned about their access to water resources. The policy issue that's highlighted in the sources is that water rights are often allocated by volume, in liters per second, rather than managing the entire hydrological system of the water body as a whole.
It's a very siloed approach.
A siloed allocation system, yes. And it tends to ignore the overall stress that's being placed on the entire ecosystem.
And when those communities raise concerns about the impacts, what's a process for ecological monitoring? Is there transparency?
This is a huge point of contention. The source material indicates a serious lack of independent scrutiny. Community members express concerns that all of the ecological reports and the impact assessments are often supplied solely by the mining companies themselves.
So there's no third-party verification.
Very little. And this creates massive issues related to the reliability and accessibility of critical environmental data. It makes it very, very difficult for local groups to effectively challenge the resource allocation decisions that are fundamentally impacting their way of life.
Okay, let's fast forward now. We've built these things, they've lived their lives. We're at the end of the life cycle, the waste problem. What happens when these panels and turbines are decommissioned after 20 or 25 years?
It's quickly becoming a massive industrial waste crisis that we haven't fully planned for.
And the biggest problem is with the wind turbines.
The most intractable disposal issue right now stems from the enormous blades of the wind turbines. These things are huge, and they're made from composite materials. Fiberglass, carbon fiber, epoxy resins, which are all bonded together.
And they're hard to recycle.
They're currently regarded as largely unrecyclable, at least economically. The difficulty and the high energy cost of separating those bonded components is the main barrier.
How big is this waste stream going to be? Do we have estimates?
The estimates are growing rapidly. Projections suggest that approximately 225,000 tons of expired blades will be added to the global waste stream annually until 2034.
225,000 tons a year. That's an enormous amount of industrial waste with no immediate sustainable solution. It is. So what are we doing with them now? What are the current methods for disposal?
We have a few, well, pretty undesirable options. Landfilling is the cheapest and easiest route, so that's where many of them go. They just chop them up and bury them. But that's obviously unsustainable for such a massive, growing, and durable volume of waste.
What about burning them?
Incineration is another route, but even when you burn the composites, it leaves behind about 60% of the scrap material as a difficult-to-dispose-of ash. The entire industry is desperately searching for a breakthrough in composite material recycling that is both economically viable and scalable.
And what about the recycling status for those critical materials we just talked about? The rare earths, the silicon from solar panels?
The situation is equally dire. Today, most disposal of solar panels still relies on landfilling. And even for the most valuable, most geopolitically sensitive materials, the rare earth elements recycling currently constitutes less than 5% of the global supply.
Less than 5%.
Yes, and this just reinforces the core challenge here. We are building an energy transition based on materials that are difficult to acquire, create toxic and radioactive waste during extraction, and are nearly impossible to economically recover at the end of their life.
So we're creating a new problem.
The need for reliable, large-scale, and environmentally sound disposal and recycling systems has to catch up immediately with the deployment rate. Otherwise, we are simply exchanging one major environmental problem for another one.
Okay, we've covered the physics barrier of stability and the material barrier of supply and waste. Let's look at what happens when a national policy ignores those physical realities. Germany's Energiewende, their energy transition, is the world's most detailed and probably most expensive case study in rapidly pursuing a high VRE system without sufficient storage or backup.
The German story really crystallizes in 2011. That's when the politically driven decision was made to phase out all nuclear power plants in the wake of the Fukushima accident in Japan.
And that decision immediately created a massive self-inflicted gap in their energy supply.
A huge gap. A gap in their supply of dispatchable, zero-emission, always-on baseload energy. They turned off the tap for their cleanest, most reliable power source.
And this is where we have to reinforce what the sources call an incredible policy blunder. If Germany had simply kept its existing nuclear fleet running, how clean could its grid have been today in 2024?
The analysis is pretty stark. Studies, including some published by major firms like PwC, show that if Germany had just maintained its nuclear fleet, 94% of its 2024 power generation could have been emission-free.
94%.
94. That nearly eliminates the need for coal and gas for basic electricity supply.
And yet the actual outcome after the phase-out was far, far less clean.
Precisely. By 2024, Germany only achieved about 61% emission-free generation. That massive, dependable hole left by eliminating nuclear was rapidly filled by increased fossil fuel-fired production, specifically hard coal and natural gas.
So they replaced non-emitting power with high-emitting power.
In order to maintain stability, yes. It directly undermined the primary environmental goal of the whole policy.
And this came at an incredible economic cost to the consumer, which is a huge part of the German narrative.
The financial burden is immense. German household electricity prices are among the highest in Europe. They're roughly 3 times more expensive than what you'd pay in the USA.
And where does that high cost come from?
A large portion of it is driven by government levies, particularly one called the EEG Umlage, which is the Renewable Energy Sources Act levy. It's a surcharge on every electricity bill that's used to subsidize the construction and operation of renewable facilities.
And how massive are the investments being subsidized by the consumer?
We're talking hundreds of billions of euros. Conservative estimates put the total investment and subsidy costs paid by taxpayers and consumers somewhere between 250 and 300 billion euro up to now.
And it's not over.
Not by a long shot. Some forecasts suggest the ultimate cost, once you factor in all the necessary grid upgrades to handle the intermittency, could exceed 1,000 billion euros, a trillion euros.
A trillion. That's an enormous financial transfer, fueled by a political decision. that the consumers are ultimately bearing.
Yes.
And for all that money, how effective was it, especially in the early stages? Did they see a big drop in emissions?
The environmental payoff was painfully slow. Despite those enormous investments, starting with the EEG law back in 2000, the data shows there was hardly any significant decrease in CO2 emissions over the following decade.
So the grid just got more expensive.
It got more expensive, not demonstrably cleaner, because the fossil fuels were always there, in the background, waiting to fill the gaps created by the intermittency of the new renewables.
And we tend to focus on CO2, but increasing the reliance on coal and gas that has other more localized health costs that directly impact German citizens.
That's a critical point that often gets missed. The policy decision to increase coal and gas reliance means higher concentrations of local air pollutants, things like particulate matter PM10 and PM2.5, carbon monoxide, nitrogen dioxide.
The stuff that causes smog and asthma.
Exactly, the pollutants that cause smog and respiratory issues. And this localized pollution contributes to significant external costs, including higher rates of premature mortality, especially in the regions surrounding the conventional power plants that had to be ramped up to support the VRE grid.
Now let's talk about the economic absurdity of overproduction. This ties right back to our bathtub analogy. When Germany has too much wind and sun, the bathtub overflows. What happens then, and why is that also a cost to the taxpayer?
This is the phenomenon of negative electricity prices. It happens on very sunny, very windy days. The VRE generation is so massive that the power flowing into the grid exceeds the minimum technical operating load.
The lowest level the grid can run at.
Right, the lowest level the grid can operate at without damaging equipment or tripping offline. Grid operators must get rid of that excess power instantly to prevent a catastrophic system failure.
And how do they get rid of it?
They literally have to pay someone to take the electricity off their hands.
They pay them.
Yes. They export the surplus to neighboring countries, often at negative prices. This means the German system pays Poland or France to take their power, and that cost of paying to offload power that nobody needs at that moment is ultimately borne by the German taxpayer and consumer through various surcharges.
So the overcapacity needed to compensate for the bad days is so massive that it results in these costly periods of enforced waste on the good days.
That's a perfect way to put it.
The sources seem to characterize this German experiment as a major warning sign. What is the final overarching lesson from their experience?
I think the lesson is that political ambition, when it's divorced from engineering reality, is not only expensive but often counterproductive. Germany's experiment really highlights the risk of pursuing a green at any cost ideology.
So, knowingly steering toward a policy with a massive financial and physical risk profile.
Yes, without having robust, scalable storage or a plan for reserve capacity. The sources argue that until some fundamental breakthroughs in physics were made, removing dependable non-fossil baseload sources like nuclear, it just guarantees a continued and in some cases deeper reliance on conventional fossil energy to keep the lights on and the grid stable.
Let's shift dramatically now to Japan. It's an isolated island nation, so for them, energy policy isn't just about the environment. It's fundamentally about survival and national resilience. Their energy framework, especially after the 2011 Fukushima accident, provides a really powerful contrast to Germany's path.
It does. Japan's policy is guided by a very holistic principle they call the 3E plus S.
3E plus S.
It stands for energy security, economic efficiency, environmental sustainability, and crucially, safety. After Fukushima, safety concerns completely dominated this discussion, and that led to the shutdown of nearly all of their nuclear reactors.
What was the immediate practical impact of that massive nuclear shutdown on Japan's energy independence? I mean, they don't have their own fossil fuels.
It was devastating for their energy security. Japan, which has minimal domestic resources, was forced to dramatically increase imports of liquefied natural gas, coal, and oil just to keep the country running.
So their import dependency just shot up.
It surged to a peak of 94% of their total energy supply by 2014. Just imagine being 94% reliant on volatile global commodity markets and vulnerable shipping lanes for your entire economy. That's a constant, nagging national security risk.
And that deep vulnerability is what's driving their long-term strategy now, even as they embrace renewables. What does their planned 2030 energy mix look like?
They're aiming for a very careful, pragmatic balance driven by that security and efficiency imperative. They're targeting about 22 to 24% renewables, which is an increase from their current 19%.
Okay.
But crucially, they are also aiming for a 20 to 22% recovery in nuclear power generation.
A recovery, so they're bringing the reactors back.
That's the plan. Achieving that nuclear target means getting approximately 30 operational reactors back online. They recognize that nuclear is the only large-scale, dispatchable, non-fossil domestic energy source they have to reduce that dangerous import dependence.
But even with that nuclear restart and the growth in renewables, they're still forecasting massive fossil fuel reliance for the next decade.
Indeed. Fossil fuel use is still expected to account for 76% of Japan's total primary energy supply and over half of its power generation in 2030.
And part of that is new fossil fuel infrastructure, right?
Yes, this dependence is so ingrained in their security planning that Japan is actually among the few advanced economies that's anticipating new coal generation capacity. They're planning to bring about 11 gigawatts of new coal plants online by 2026.
That seems like the very definition of locking in high-carbon infrastructure for the long term. Why coal? It's the dirtiest fuel.
It's a cold calculation based on cost, security, and stability. Coal is plentiful on the global market, it's easily shipped, and it's reliable for baseload power.
But what about the emissions?
Well, Japan has one of the world's most efficient coal fleets, using very advanced technology. But the environmental comparison is still stark. Even a highly efficient modern coal plant emits over 700 grams of CO2 per kilowatt hour.
And how does that compare to gas?
It's nearly double the emissions of a modern natural gas-fired plant, which is typically in the range of 300 to 500 grams. So they were making a very deliberate trade-off. They're prioritizing security and stability over the absolute fastest path to decarbonization.
This high reliance on conventional power, it leads to this interesting concept the source is called the electric vehicle carbon paradox.
Yes, this paradox neatly illustrates how cleaning up one sector of the economy, like transportation, doesn't necessarily achieve a true environmental gain if the other sector, in this case, power generation, remains dirty.
How does that play out in Japan?
Japan is heavily promoting the electrification of mobility. They're aiming for electric and plug-in hybrid vehicles to capture at least 20% of the new car market share by 2030.
So the roads will look greener. You'll see more EVs. But when those cars plug in at night, they are, in effect, burning imported coal and natural gas.
That's the paradox in a nutshell. Because Japan's electricity mix is still so carbon intensive, the environmental gain from EV adoption is fundamentally capped.
What are the numbers?
The sources note that even in Japan, an EV will still emit 20 to 30% less CO2 over its lifetime compared to a conventional car. So there is a benefit. But that benefit is far, far smaller than in a country like France or Sweden with an already decarbonized grid.
So it proves the point we've touched on before.
It proves that the environmental cleanliness of an electric vehicle is entirely dependent on the carbon source powering the charger. You absolutely must clean the grid before you can truly clean the roads.
We've covered a tremendous amount of ground in this deep dive. We've gone from, the physical impossibility of seasonal storage all the way to the geopolitical reality of critical mineral scarcity. I think our findings reveal that the renewable transition faces three immense hurdles.
It really does. There's the physics barrier of grid stability, the material barrier of mining and waste, and then this policy barrier of security and cost.
And the core insight, it seems to me, is that this intermittency problem, it's a financial and engineering constraint that you just can't wish away.
You can't. The need for storage is astronomical. As we said, up to 120 terawatt hours for a single country like Germany. That's a scale that current technologies simply cannot meet.
And until that storage is available.
Until it is, that physical requirement for 20 to 25% rotating mass means that if you eliminate dependable, dispatchable sources like nuclear, it almost always results in a greater and often more expensive reliance on conventional fossil fuels to maintain system stability and prevent blackouts.
And this transition, it comes with all these hidden external costs that we're only just beginning to measure. The geopolitical dependence on rare earth supplies in countries that, frankly, don't share our environmental standards.
The devastating local pollution from mining critical materials.
And the rapid creation of this growing industrial waste crisis, driven by currently unrecyclable components like those composite turbine blades.
And the experiences of both Germany and Japan really confirm this critical reality. Massive investments in intermittent renewables, if you deploy them without corresponding breakthroughs in storage or dependable non-fossil baseload, they place immense financial burdens on consumers.
Hundreds of billions in the German case.
Hundreds of billions, and they often necessitate fossil fuel support, which means you fail to significantly reduce emissions, at least initially, and you can even increase local air pollution in the process.
So to wrap up, here is our final provocative thought for you to carry forward. If stability is the one non-negotiable, and the physical world dictates that 20 to 25% of our grid power must be dispatchable and always on, should the focus of the green transition be less on the massive, subsidized deployment of variable sources that require unfeasible amounts of storage, and more on ensuring that the dependable, always-on backup power that we need for a stable grid is definitively non-emitting?
Whether that solution is advanced nuclear or next-generation geothermal or expanding hydro where possible.
Something to think about next time you hear a simple narrative about what is a deeply complex energy policy. Thanks for coming along on this deep dive with us. Remember to follow us on your favorite podcast platform.
And we'll see you on the next dive.